Hello everyone, welcome to today's lecture. Last week we talked about ANOVA, which is used to study the relationship between a numerical response variable and a categorical explanatory variable with more than two categories. This week, I'll introduce two hypothesis tests, correlation and regression. Both of them are used for the scenario where two numerical variables are involved. Now let's start with the correlation. In the real world, we often hear people say two things are correlated to show there is some kind of relationship between the two. For example, here, studies find having more online social connections is correlated to reduced mortality, indicating online social connection may have potential impact on mortality. Another example here, showing stress from childhood may correlate with dysfunction in blood regulation, also indicating there is a relationship between the two. Now back to biostats. Correlation is a hypothesis test which is used to examine the relationship between two numerical variables. Here we have an example where we summarize the number of recorded failed health inspections in city food service establishments per 100,000 population and the number of hospitalized cases of E. coli per 100,000 population from different cities across Canada. In this case, we have two numerical variables and we wonder if there is a relationship between the two. First, let's create a scatter plot to explore the data. Here, the x-axis is the number of failed inspections, and the y-axis is the number of hospitalized cases. Only by eyeballing we can somehow see a crude trend here. As the number of failed inspection increases, the number of hospitalized cases also increases. However, we are not able to draw a conclusion just by eyeballing. Therefore, the correlation will help us better examine the data. The test statistic in correlation is R, which is called the correlation coefficient. We use it to describe the relationship between two numerical variables. The correlation in a population is described using the Greek letter rho. Usually we estimate rho using the correlation coefficient in the sample, which is R. The math for correlation is to summarize the scatter of the points. Correlation measures the tendency of two variables to covary along a line, although it doesn't plot the line. It is able to show how strong the relationship is and also the direction of the relationship. Here, I show four scatter plots created from different data and the correlation coefficient estimated from each data. First, in the figure on the left, so it's this one, the dots are randomly scattered in the graph area, and we are not able to see a trend or a line here. This kind of data has an R value of 0. Now let's move to the second graph. So it's the graph here. In this graph, we start to see a linear trend, although the trend is not that clear. In this trend, we can see where x increases, y also increases. Here the R is 0.5 in this graph. In the third graph, so it's this one, we can see a decreasing trend, and the data is less scattered compared to the second graph. So R has a negative value, but the absolute value of R, 0.7, is larger than 0.05. Sorry, larger than 0.5. In the figure on the right, so it's this one, the data is even less scattered. we can see a clear increasing trend here. And the R for this data is 0.9. From the four graphs, we can see the absolute value of R reflects the amount of scatter. The larger the absolute value is, the less scattered the data is around the trend line, although we don't fit a line in the correlation. Moreover, R being positive or negative indicates the direction of the association, where positive means an increasing trend, while negative means an decreasing trend. In the correlation analysis, R will remain the same when X and Y change axes. Now I will show you more examples of data on the scatter plot with different values of R. Okay, so here in this one, it has an R value of 0. What the dots shown here is like an even cloud. We're not able to see a trend here. Here in this one, it has an R value of 0.42. We can see an increasing trend line here, although the dots are somehow scattered around the trend line. Now the R value increases to 0.78. The dots become less scattered around the increasing trend line. Now, when R goes to 0.97, and the dots are even less scattered around the trend line. Finally, when we have an R value of 0.99, the dots almost form a line themselves. Here is just to show when R is negative, we can see a decreasing trend. The value of R ranges from -1 to 1, where 1 means a strong positive linear relationship, and -1 indicates a strong negative linear relationship. When R equals to 0, it means there's no linear relationship, or it can be a nonlinear relationship. Here, I include the guidance on how to interpret the absolute value of R, where 1 to 0.19 means very weak linear relationship. 0.2 to 0.39 means a weak linear relationship. 0.4 to 0.59 is moderate. 0.6 to 0.79 is strong. And finally, 0.8 to 1 is very strong. By far, we have learned what is R and how to interpret R. Now let's take a look on how to calculate R. Here shows the formula to calculate the correlation coefficient, which is R. It's estimated as the sum of cross products divided by the square root of sum of squares. To do the calculation, you'll need each value of X and Y, as well as the mean of X and mean of Y. Now, let's do the calculation using the example here. In this case, we studied the relationship between loss of sleep and performance on the exam. We want to know whether loss of sleep will influence the exam performance, and we created an imaginary sample of 31 students. The data is shown here in the scatter plot, where x-axis is the sleep deficit and y-axis is the exam performance. The sleep deficit has both negative and positive value, where negative value means hours lost and positive value means hours gained. exam performance is assessed in percentage. Although the dots are pretty scattered in the graph, we can still see an increasing trend here. Let's start with the null hypothesis and alternative hypothesis. Our null hypothesis is sleep deficit and exam performance are not correlated, or rho equals to 0. And the alternative hypothesis is sleep deficit and exam performance are correlated, or rho is not 0. We use rho in our hypothesis because it's the relationship in population that we are interested in. In our case, we collected a sample from the population and we want to use the correlation coefficient estimated from our sample, which is R, to get an idea about rho in the population. Now, let's do the calculation together. In previous slides, I already showed R is estimated as the sum of cross products divided by the square root of sum of squares. Here, I did some transformation of the formula to simplify the process. Now, what we need here is sigma xi yi, which is the sum of the product of x and y, sigma xi, which means the sum of all x value, sigma yi, which is the sum of all y value, and sigma bracket xi squared, which is the sum of all the squared x value, and sigma bracket yi squared, which is the sum of all squared y value, and finally n, which is the sample size. You can pause here and do your calculation. I will show you the results in the next few slides. Okay, so here are all the calculated value for the components necessary to estimate correlation coefficient. And with this value, we calculated this component from the formula for the R is 2.796, and this component the value is 16.245, and for this component the calculated value is 1.6289. Now, let's add these values into our R formula to get the actual value of R, which is 0.5435. Based on this calculated R value, we can see a moderate positive linear relationship between sleep deficit and exam performance. Now, we have calculated our R value. What will be our conclusions on our correlation test? As I mentioned in previous slides, our null hypothesis is about rho, which is the correlation coefficient in the population. And we tested by estimating R from our collected sample. It's tested by looking at the sampling distribution of R to the test hypothesis that the mean of the sampling distribution of R is 0. So, if rho equals to 0 in the population, as stated in the null hypothesis, R in our sample will be normally distributed with the mean of 0. Knowing this as the background information, we can calculate the t-value from our sample and compare this calculated value to the critical value in the t-distribution table and draw a conclusion from there. The t-value is calculated as R divided by standard error of R, and the degree of freedom is n minus 2. the t-distribution is the same one as we learned in t-test. Now let's do the calculation. Here we have R value of 0.5435. The standard error of R is calculated as square root of 1 minus R squared divided by n minus 2. And we get a value of 0.1558 as the standard error of R. And T is calculated as R over standard error of R, which is 3.49. And the degree of freedom is n minus 2, which is 29 in this case. Now we go to the t-distribution table and we find a critical value of 2.045 with degree of freedom of 29 at the two-sided significant level of 0.05. Because our calculated t is 3.49, which is larger than 2.045. Therefore, our p is less than 0.05. So we reject the null hypothesis, and we can say sleep deficit and exam performance are correlated. Now, back to our health inspections example. Based on our data, we calculated an R value of 0.72, meaning the number of failed inspections and the number of hospitalized cases are positively correlated. Now, let me introduce another test statistics in correlation, which is R squared. You can see we use the capital R here. Mathematically, if you square your R value, you will get your R squared value, which is easy. So the R squared is called the coefficient of determination. It shows the proportion of variation in your response variable, which can be explained by the variation in your explanatory variable. Now let's calculate the R squared value in our example. Basically, it's just to square the R, which is 0.72. Then we squared it, and the R squared value we can get is 0.5184. So it means 52% of the variation in number of hospitalizations is explained by the variation in number of failed health inspections. Now let's do a bit more practice. Please calculate the R squared value for each correlation coefficient here. You can pause here and I will show you the results in the next slide. Here are the calculated R squared value. For the first one, it means 12% of variance in Y is explained by the variance in X. The second, 66% of the variance in Y is explained by the variance in X. And the last one, only 1.4% of the variance in Y is explained by the variance in X. Now, let's finish our correlation test on the health inspection example. To test the significance of R, we'll need to calculate the standard error of R and the degree of freedom. The formula for the standard error of R and T are shown here. You can pause and do the calculation on your side. When you're done, you can continue playing. So here, the calculated standard error of R is 0.1683, and the calculated t value is 4.28. Now go to the t-distribution table and find out the critical t-value. You can pause here. I will show you the number in the next slide. So the critical value with degree of freedom of 17 at the two-sided significant level of 0.05 is 2.11. Now we know the calculated t, which is 4.28, is larger than the critical t, which is 2.11. So what do you conclude on the null hypothesis? You can pause here, and after you make your choice, press continue. So the correct answer is D. When the calculated t is larger than the critical t, p-value is less than the significant level, which is 0.05. So we can reject the null hypothesis. Then we can say there is a correlation between the number of failed health inspections and the number of E. coli hospitalizations. There are certain assumptions of the correlation which must be met for the test to be valid. First, it must be a random sample. Second, X is normally distributed with equal variance at all value of Y. And on the other side, Y is normally distributed with equal variance for all values of X. So I'll expand on this test assumption topic in our lecture next week. So I won't get into too much detail here. Now we have learned correlation, and we know it's used to test how tightly points fit to a line, although we don't draw a line with correlation. What if we want to draw this fitted line? To do so, we'll need to run a regression analysis. With the fitted line estimated from regression, we are able to predict the value of y from the value of x. In other words, predict the value of the response variable from the value of the explanatory variable. And linear regression assumes that the association between x and y can be described by a line. The relationship between x and y estimated by linear regression can be expressed in the formula here, which is y equals to alpha plus beta times x. This equation shows the simplest linear relationship between x and y with only two parameters, alpha and beta. As the regression model gets more complicated, more components of the equation can be added. However, in our class here, we'll focus on the simplest form. We call this the simple linear regression. The two parameters of the equation are alpha and beta, but be careful. These are not the same alpha and beta when we talk about like type 1 and type 2 error. Here, the alpha is the intercept, while beta is the slope. We'll talk about the concept of intercept and slope in the next few slides. Before that, in the equation where alpha and beta are used, it shows the linear relationship between x and y in population. However, in the sample we collect, we use A and B to replace alpha and beta in the equation to show the linear relationship. Before we move to an actual example, first let me introduce the concept of residual. So it's the difference between actual y value, which is the yi here, and the predicted y value, which is the yi hat here. For example, in the figure here, The 4 black dots represents the 4 actual measurements. So these 4 black dots is the actual measurements. And we run the regression and we draw a fitted line across the dots. So this one is the fitted line. And based on the equation estimated by regression, we are able to calculate the predicted y value at each value of x. And the predicted y is the y hat here. So they are the red dots on the fitted line. So these are the predicted y value here. And the distance between the black dots and the red dots are the residual. So it's the distance between the black dots and red dots. So it's this distance. These are the residual. Now let's look at our example. In this case, we collected soil samples near an old lead processing plant. We recorded the distance from the plant, and we measured the concentration of lead in the soil. So this is the distance from the plant in meters, and this is the soil lead concentration in parts per million. First, let's think about these 3 questions. What type of variables are these? And which one is the explanatory variable and which one is the response variable? You can pause here and press continue when you have your answers. Okay, so here, both of the 2 variables are numerical variable, and the explanatory variable is the distance from the plant, and the response variable is the concentration of lead in the soil. So for this one, we will use regression to analyze the data. So first, let's visualize the data using a scatter plot. So here is the scatter plot we create, where distance from the plant is on the x-axis and the lead concentration is on the y-axis. And usually, we'll have our independent or explanatory variable on the x-axis and our dependent or response variable on the y-axis. And each dot here represents a measurement, and it has its own coordinates. For example, here, this point has a x value of 190 and a y value of 610. And based on the trend, it looks like there's a linear relationship between the 2 variables. Now we draw a line here, but how do we know if this is the line which best fits the data? So when the fitted line minimizes the sum of the squares of the vertical distance from each point to the line, also known as the residual as we talked in previous slides, we say it is the best fitted line. We call this the least squares regression. In the figure here, the red lines represents the residuals from each x value. The red lines here. The fitted line here minimizes the sum of the squared residuals. Here, we draw another line across the data points. However, this is not a line of the best fit because it doesn't minimize the sum of the squares of the residuals. So, to summarize, the simple linear regression used the least squares regression to minimize the sum of the squared residuals, where y is the observed value and y prime is the value on the line for a given value of x also known as the predicted y value. Each different y minus y prime, also known as the residuals, is squared to prevent the positive and negative differences canceling each other out. The fitting line can be expressed as the y equals to a plus b times x, where a is the intercept and b is the slope. The intercept, a, is the value of y when x equals to 0. It is also the cross point between the fitting line and the y-axis. The slope, b, also known as the regression coefficient, is the rate of change in y per unit of x. Its sign shows the direction of the relationship, where positive value means y increases as x increases, and negative means y decreases as x increases. The slope may have a value from negative infinity to positive infinity, and the slope of 0 means no relationship between x and y. Now back to our example. The equation of the best fitted line is y equals to 778.05 minus 1.1927 times x. So here, the intercept is 778.05. It is the concentration of lead in the soil immediately surrounding the plant, which means the distance from the plant is 0. And the slope here is minus 1.1927, which means for each meter further away from the plant, the soil lead concentration decreases by 1.1927 parts per million. The formula to calculate the slope is shown here. It estimated as the sum of a cross products divided by the sum of squares of x, where xi is each value of x and yi is each value of y. X bar is the mean of all x value, and y bar is the mean of all y value. After the slope is calculated, the intercept can be estimated as y bar minus b times x bar, where y bar is the mean of all y value, and x bar is the mean of all x value. Now, let's use another example to do the calculation of the slope and intercept. Back to the 50s and 60s, there were many above-ground nuclear bomb tests, which might have left a radioactive signal in developing teeth. So is it possible to predict a person's age based on their dental carbon-14? Since both two variables here are numerical, and the scatter plot somehow shows a linear trend, let's do a regression to test the relationship between radioactivity in the teeth and the age. In this example, we took a small subsample of 14 measurements from the original study, and the amount of dental carbon-14 and the date of the birth is listed in the table here. In this case, the amount of carbon-14 is the explanatory variable, and the year of birth is the response variable. So carbon-14 is x, and the year of birth is y. Here I list all the components necessary for the calculation of the slope, including sigma x, which is the sum of all x value, sigma y, which is the sum of all y value, and the sum of all squared x value, sigma x squared, and sigma xy, which is the sum of the products of xy, and the sigma y squared, which is the sum of squared y value or y value, as well as n, which is the sample size, and x bar is the mean of all x value, and y bar is the mean of all y value. Here, I show the formula and its transformation for the slope. You can pause here and do a calculation. I'm going to show you the results in the next slide. So the components of the numerator, so it's the numerator here, has a value of minus 23,393. And the component for the denominator has a calculated value of 439,226. And we divide the numerator by the denominator, and we have a slope value of minus 0.053. Now let's calculate the intercept, A, using y bar, x bar, and the slope we just calculated. You can pause here and do the calculation on your side. I will show you the results in the next slide. Now, the calculated intercept is 1992.2. Now we have the equation of the best fitting line here. So let's do some prediction using this formula we just have. So here, let's predict y from x. So in this case, if a cadaver has a teeth with the dental carbon-14 content equals to 200, so what does the regression line predict its year of birth to be? You can pause here, and I'm going to show you the results in a second. Okay, so here is the results. So if you add the 200 as the x value and do the calculation, the predicted y value will be 1981.6. Now let's do more practice. Please calculate the predicted year of birth for each of the following levels of dental carbon-14. You can pause here and press continue after you finish your calculation. So here are the results. For dental carbon content of 16, the predicted year of birth is 1989. For 239, its calculated value of y is 1980. For carbon-14 of 87, we got the year of 1988. And finally, for the content of 1134, the predicted birth year is 1932. Although we can use the best fitting line to predict y from x, it's usually unwise to extrapolate beyond the range of the data, because the regression we do is only based on the data within the range. We don't know what is the relationship looks like beyond the range of the data. Their relationship may no longer remain linear beyond the range. Even if they remain linear, extrapolating beyond the range may still result in numbers which may not make sense in the real world. For instance, here, we have a regression line where numbers of species of fish is predicted by the area of a desert pool. The data goes up to around 9,000 square meters for the area of the pool. If we extrapolate beyond that range and we asked how many species might be in a pool of 50,000 square meters, which is far beyond the range we have here, we could guess about 20 species from the regression equation. However, in the real world, the total number of fish species in the desert area might already be less than 20. Now let's talk about how to test the hypothesis about regression. We already learned that the simple linear relationship between the two numerical variables in the population can be defined as y equals to beta times x plus alpha, where alpha is the intercept and beta is the slope. To estimate its relationship in population, we took a representative sample from the population and we fit a regression line in our collected sample, which is defined by the y equals to b times x plus a. So here, b is our estimate of beta and a is our estimate of alpha. As we already introduced in previous slides, when slope is 0, it means there is no relationship between the two variables. Therefore, in our hypothesis test about regression, it is based on the slope. So we want to know in our population whether the slope, beta, is 0 or not. So in non-hypothesis, the slope is 0, meaning there is no relationship between the two variables. In alternative hypothesis, beta is not 0, meaning there is a linear relationship between the two variables. Our estimated slope follows a t distribution. This is the same t distribution as we learned for t-test and also correlation. The test statistic, t, is calculated as b minus beta 0 divided by the standard error of the slope. Here, b is the slope we estimated in our sample. Beta 0 is the population slope we try to estimate in non-hypothesis, which is 0. Here is how we calculate the standard error of the slope. It is the square root of mean squares of the residual divided by sigma bracket xi minus x bar bracket squared. The mean squares residual is calculated as the sum of squares over the degree of freedom residual. To calculate the sum of squares residual, we need to start with calculating the sum of squares total and the sum of squares regression. The formula to calculate SS total and SS regression is shown here. We'll need each value of y and the number of total sample n to calculate the SS total. For the SS regression, what we need is b, our estimated slope, xi, each value of x bar, which is the calculated mean of all x, yi, which is each value of I, and finally y bar, the estimated mean of all y value. Since the SS total is the sum of SS residual and SS regression, once we have the SS total and the SS regression, we can calculate our SS residual by subtracting SS regression from SS total. And here, the degree of freedom for residual is n minus 2. Now, back to our radioactive teeth example. According to our collected data, the calculated SS total is 1339.7, and the SS regression is 1239.8. Here, SS residual equals to SS total minus SS regression. So the calculated SS residual is 99.9. The degree of freedom residual is n minus 2, where n is 16. So we have 14 here. With the SS residual and DF residual, the calculated mean square residual is 7.1. Now, follow the formula for the standard error of the slope. We can get a value of 0.004. Now, let's calculate our t-value. The calculated slope, b, is minus 0.053. And as we mentioned before, beta 0 is the population slope in null hypothesis, which it has a value of 0. Here, our b has a negative value. However, the negative sign only indicates the direction of the relationship, and what we want to know here is whether the slope is 0 or not. So we take the absolute value of t, which is 13.25. So this is our calculated t-value. After going through the t-distribution table, the critical t-value with the df of 14 and the two-sided significant level of 0.0001 is 5.36, which is less than our calculated t-value. So our p-value is smaller than 0.0001. We can reject the null hypothesis. The slope doesn't equal to 0. And there is a statistically significant relationship between dental carbon-14 and the year of birth. Here are the assumptions of the regression. Again, it must be a random sample. Second, it assumes a linear relationship between the two variables. Third, y should follow a normal distribution, and it must show equal variances for all values of x. I'm not going to get into too much detail here. So here comes the end of today's lecture. In this lecture, we introduced the two types of hypothesis tests, correlation and regression. Both of them are used to assess the relationship between two numerical variables. Next week, I'll expand on the test assumptions we learned in this class. I'll also do a review of all the tests from this class. Take care and see you next week.